Hello and welcome to Lecture 6. So, if you recall, we started this course with two problems that we wanted to try and solve, and that was to find the slope of the tangent to some particular graph, and we chose the graph of x squared, and we wanted to find the velocity of a stone that we dropped from a tower. And to do that, we did this procedure of creating a table and numerically trying to see what happens at a smaller and smaller scale, and that was to motivate this concept of limit. Now we've learned about limits, now we are practiced at limits, we can go back and solve these problems and actually understand the exact answer. So this is the payoff, this is why we were learning about limits. So let's do that. So we're on 2.7, differentiability. So, what was the first problem? So, the first problem was to find the tangent to a function, the tangent line to a function at a particular point. So this could be our function, and we have some particular point, and we are trying to find the tangent line to this function. So that's the line that goes through this point with the same slope as the function in that particular point. And what are we going to do to solve that? Well, we did this table and we got closer and closer, and we considered the specific case of f of x is equal to x squared, and we took the point p11, right? Because when x equals 1, it goes through 1, right? So, let's draw a little picture, clarify what we were doing. So here we are, P11, and we said, okay, this is P11, but if we move forward a little bit to say Q of x squared, then we can consider the slope of the secant line joining these things. So we define MPQ is the slope of the secant line, and we found that this was just equal to x squared minus 1 over x minus 1, because if we look more closely at this thing, we blow this up, so blow up what's inside this circle to over here, what do we see? We have this being P11, this being Qx x squared, right? This is the secant line connecting them. Maybe that's not clear enough. Let's try it with this. It's a lot better. And we have a triangle, okay? And what is this side? This will just be x squared minus 1. And this side will just be x minus 1. Change color, so this is x squared minus 1, and this is x minus 1. Again, not very clear, so let me rewrite that. X squared minus 1, x minus 1, right? So, the slope is how far up or down we go, divided by how far along, and it'll be given by this expression, right? And what we did is we let x get closer and closer to 1. So here is 1, and here is x. Yeah? Because we can see just from this picture that as we let x get closer and closer to 1, the slope of this hypotenuse is more and more close to the slope of the actual graph of the function. Yeah? So then we took just a table of values and then tried to calculate it. But we've also learned from a previous lecture that if we try and do that, then we easily get things that just give us false information, right? We had this example where for small values it tended to 1 over 6, but if we took even smaller values it seemed to be actually 0. So we don't trust numerical tables anymore. We have developed this machinery that allows us to analyze limits. So we want the limit as x goes to 1 of this quantity. And this is a perfectly nice rational function. 1 obviously is not inside its domain. We can't just plug in the value 1 into this. It's not continuous. It's not even defined at 1. So what are we going to do? We just do some algebra. This is the limit as x goes to 1, x minus 1, x plus 1 over x minus 1, and the x minus 1 cancels because as x approaches 1 it's not actually equal to 1, so this is the limit as x goes to 1 of just x plus 1, which is 2. So we have that the slope infinitesimally at this point 1 is just equal to 2, right? And then it was just getting the tangent line, right? So recall we have this convenient way of thinking about it. If you just write t of x as 2, the slope x minus the x coordinate, which is 1, plus the y coordinate, then this for sure will give us the tangent line that goes to the right point, because when you put an x as 1 inside this entire part here just cancels and we just end up with 1 overall, right? And if we just expand that out, we have 2x minus 1, which is what we found before. So this part's the same as we found before, except now we know for sure that this is the slope. Yeah? Cool. So let's consider the other problem we were thinking about, and that was dropping the stone from the top of the Secant tower. So example. So A. Actually, let's write the question in first. A stone is dropped from Secant tower, which is 450 feet high, or 450 meters high. And we have two questions. First question, what is the speed? What is the velocity? After 5 seconds. And the second question is, what speed is it going when it hits the ground? Or what velocity? When it hits. Okay? All right, solution. So recall that we have this very nice formula all the way back from Galileo. So this is our tower. This is us on the top of a tower dropping the stone, right? And after t seconds, it drops down by 4.9 times t meters, right? Which is a formula we get because gravity is more or less constant near the surface of the Earth, and if it's a stone, there isn't much wind resistance, air resistance. This is basically fairly, well, it's a very good formula for this particular physical setup. Okay. Oh, I shouldn't write it like this. I should write S of t. Okay, this is how far we've dropped after exactly t seconds in terms of meters. And we could be, for example, here, S of 5 after 5 seconds, right? And if we want to know how quickly we are dropping, what is the velocity, what we did before was we just went forward a little bit in time to, let's change colors, say this point here, which is just S of 5 plus h, right? And then we said, okay, then the average velocity over the time interval is just how far it travels divided by the time. So it's going to be S of 5 plus h minus S of 5 over h, right? And that isn't giving us the real velocity, but as h gets smaller and smaller, it gets closer and closer to the instantaneous velocity. This we discussed in the first class, right? So again, this is now something we can give a meaning to. This is taking the limit as h tends to 0. And let's actually do something even more general. So, because we'll need this later. More generally, the velocity at, at time t is given by this. It's going to be the limit as h goes to 0 of s of t plus h minus s of t over h. Exactly the same reasoning, except now we're doing it for an arbitrary time t instead of some specific time 5. Okay, but now we can put in what the formula for this is. So we have 4.9 t squared. Let's just factor out the 4.9 straight away. And then this is the limit as h goes to 0 of t plus h squared minus t squared over h. And then we just do the algebra. That's, that is 4.9, the limit as h goes to 0. So if we expand this out, let me just do it all the pieces. So we're going to have t squared plus 2t times h plus h squared minus t squared over h. And as you can see, the t's are going to cancel. Sorry, the t squareds are going to cancel. This cancels, this cancels. And as h goes to 0, we don't care about h being 0. H is going to 0. It's not 0, right? So in the limit, again, we don't care about the actual value at the point itself. That's not part of the limit. We care as the thing approaches that point, right? So h is never 0 in the limit. It's as h goes to 0. So we can cancel this h. So this is just 4.9, the limit as h goes to 0. And cancelling the h, we're going to have just 2t plus h. And that's just going to be 4.9 times 2t, right? Because the h is just going to vanish. So that'll be 9.8 times t, right? Cool. So at t equals 5, that should be 49 meters per second, which is what we found before, 49 meters per second. Okay, so that answers part A, right? Now for part B. So if we go to this little picture here, we have a general formula for the velocity of the dropping stone at any moment in time. So we need to find the time it actually hits the ground, right? But we know that this tower is 450 meters high. So a little bit of thinking will give you the right thing to do, which is to find the time when we hit the ground, which we can do just by setting s of t to be equal to 450, right? And this we can solve, right? So this is 4.9 t squared equals 450, which is the same as saying that t is equal to the square root of 450 over 4.9, which is, to one decimal place, it is 9.6. So after 9.6 seconds, we hit the ground. Yeah? So the velocity at t equals 9.6 is, we just put it in this formula, is 9.6 times 9.8 meters per second. And let's see what that actually is. That's 94 meters per second. Cool. So, if you were standing directly here, trying to very carefully measure the velocity just before it hits the ground, you'd get a more and more accurate reading if you positioned your sensor just a bit above the ground and the other one just a bit beneath it, right? And then you record the time it passes the first sensor and the time it passes the second, and you have the distance between the sensors and you divide by the time. That's how you try and accurately measure this, right? And you would find that it is incredibly close to 94 meters per second. And the more accurate your measuring equipment, the closer it would seem to 94 meters per second, right? So that back in the day was really astonishing because, again, we just know the initial conditions. We know that we dropped it from a height of 450 meters. That's all we know. And early scientists would try and test this with the best stuff that they could, which by modern standards wasn't very good. But they would try and test it, and as their technology got better, as their clocks, stopwatches got better, as their ability to have some kind of sensor of some kinds of photographic equipment, whatever they were doing, as that improved, all that they found was they got a better and better fit to what this formula gave. So actually for a long time, physics was thought to be a dead subject. It was thought it was completely, well, physical world was completely understood from Newtonian mechanics. And that was a reasonable thing to think, I guess, in the 19th century because, or maybe a bit before, because yeah, everything just seemed to be more and more closely following Newton's laws. And once again, this is an extremely powerful thing. This is knowing predictively exactly what's going to happen in the future with extremely good accuracy. Now with our better understanding, we know a number of things. We know, I mean, they knew even that there was wind resistance, but it didn't have a big effect. And we know that gravity is not exactly the same at all heights. I mean, they knew that too. So this isn't the exact formula, but you have to get pretty good instruments to have any variation from this. So this was exciting stuff in the beginning of the scientific era. Okay, good. So that is what we can do with limits. No more approximations. Now we have the real answer. All right, so what are we actually doing here? Well, we are using a concept called the derivative of a function. So derivative, which is one of the most important concepts. Derivative. So if we have a function f, which is something, it's giving you something. So in this case, s is the distance from where we drop the stone, but it could be anything, right? It doesn't have to be distance, doesn't have to be whatever. It could be some quantity, but that quantity depends on some other quantity, right? So in this case, the other quantity depends on its time, right? It's moving with respect to time. But again, it doesn't have to be. So we have some quantity which depends on some other quantity. Yeah. Then the derivative is the thing that records or quantifies the rate of change of the quantity in f with respect to the change in the quantity in x. Okay. One of the ways to describe calculus is it's the mathematics of change, and the simplest and first notion of that is the notion of derivative, which records the first information about how the quantity f changes with respect to the quantity x. Okay, and as always, the picture is the clearest way to express that, and the picture is the one that we've already been discussing. So if we plot f on a graph, okay, so this is quantity f, whatever it is, and this is x, okay, then the derivative at some particular point a is indeed given by the slope of the tangent line at that particular point, okay, at the point a, f of a, yeah, because that slope gives the rate at which f is changing as we move x along, right? So in this picture I was talking about the slope of this hypotenuse is how far up or sometimes down we go compared to how far along, i.e. that's the same as saying it's the change in f over the change in x, right? Or it's how f changes with respect to x. And nearly everybody has seen some calculus before. You've heard of derivatives. You've calculated derivatives. The first thing we want to do is have a very clear picture of what it means. And I'm going to erase the board because it's such an important picture. I want to start with a fresh board. So that's what we're talking about coming up. Okay. Given function f, the derivative f prime of a is defined as follows. So I'm going to define it, and I'm going to draw the picture that clarifies it just afterwards. Okay, what's the picture? So we have some part of the graph. Okay, here is a, f of a, right? And here is x, f of x. And we draw this triangle like this, okay? So that we see that this base distance, or this base length of the triangle is a minus x. This is f of x minus f of a, yeah? So the slope of the hypotenuse is how far up or how far down we go divided by how far along, is exactly this quantity right here in the brackets, right? And as we let x tend towards a, this thing tends towards the infinitesimal slope of the graph at a, right? And from the picture, this is completely making sense. If any of you know calculus and were just tasked with coming up with some expression that records the slope of the graph of some function, some programming task or whatever, you might think about it for a little bit, maybe a day or something, but you'd all come up with something like this, right? This is the natural thing to do, yeah? And you'd all understand that as x gets closer to a, this thing gives a better and better answer as the actual slope of the function, yeah? And another way we sometimes write it is like this. The limit as h goes to 0, f of a plus h minus f of a over h. And it's exactly the same thing, except now we're letting x be a plus h. So in other words, i.e. a plus h equals x. Yeah? And if we do that, then the base length here is just going to be h. And this thing will just be f of a plus h minus f of a. Yeah? That is if this limit, which is the same as this limit, exists. Which it doesn't always have to, right? And we'll talk about that later. There are many instances where this thing doesn't exist. But if this thing exists, then this quantity, f prime of a, is well defined, and that is the derivative. This number is the derivative, okay? And as you can see, if the function is going up, if it's increasing, then this quantity will be positive, and then if we are going down, this quantity will be negative, right? Because then f of x will be less than f of a. You know? Cool. All right, so that is the concept of derivative. And that is what we've been doing, right? So when we took the slope of the tangent line to x squared, we took exactly this kind of expression, and we just took the limit, and we found the limit was 2x, right? In other words, we found that the derivative of x squared was 2x, which is something you guys know anyway, right? When we were talking about how quickly the stone dropped was going at a certain time, well, if you think about what we were doing, we had the position function, right, which was s, and we had time, the position depending on time. So we're recording the rate of change of position with respect to change in time, which you guys know is velocity, right? Which brings me to something I've said before, but now hopefully it's clearer. The concept of derivative is in everybody's head. It's a natural concept, like addition is a natural concept in everybody's head. You can't think about the world unless you have the concept of velocity, which requires the concept of taking a limit and actually taking a derivative of a function. So I guess quite a small minority of the planet actually know calculus, but everybody thinks they know what it means to say that a car goes at whatever, 60 miles an hour. If you generally do know what that means, then you are actually doing calculus. So everybody is doing calculus, like it or not. Everybody will probably claim they know what it means for a car to accelerate. But what is acceleration? Acceleration is how much faster the car is going. In other words, it's the rate of change of velocity of the car, right? Which again is taking the derivative. It's the rate of change of one quantity in terms of another. You know? So calculus isn't some kind of exotic thing that just a few strange people need to know. It's part of any educated person's mental toolbox to just understand basic things like this. And as we go further in this, you'll see there are many things that are understandable or need to be understood with this language, and are just horrible to try and express or think about clearly without this language, without this stuff. So yeah, in some future modern age, utopian age, my guess is that everyone will learn calculus just like everybody learns arithmetic or learning to read and write, because it's basic stuff. I mean, it's basic fundamental stuff that you just need to be a well-functioning, educated person. All right, enough speech making. So this is the concept of derivative, okay? And this is what we've been doing, even though we haven't explicitly defined it before. Now, when I was in high school, I learned derivative as some kind of, I learned taking the derivative, some kind of mechanical procedure which I applied to various functions. I knew that when you applied it to whatever, x to the 3, it became 3x squared. When you applied it to whatever, square root of x, it becomes a half, x to the minus a half. When when he applied it to sine, it became cosine. That's what I knew. And maybe someone showed me this picture. I mean, I think it did happen, but I don't think I saw it twice. And I certainly had no conception that this picture had anything to do with that, the mechanical procedure that I was told about, what I was taught and had to practice. So this is such a fundamental thing that we try and make sure that everybody is clear on this definition of derivative, and we try and test it. And one of the ways we test it is by making, in homeworks and in exam questions, making students actually calculate derivatives from just this definition. And we've already done this for the x squared, but we can actually do this actually we can do this for any function, but it just becomes more and more difficult. But a reasonable question is for some not particularly difficult function to actually calculate this on first principles, calculate the derivative, and you're going to be practicing this. It's a worthwhile thing to do, and that's what we're going to do next. We're going to do an example of that. So we are going to take the function f of x is 1 over square root of x, and we're going to find the derivative, if it exists, at some arbitrary point a. So the question is, find f prime of a. Okay, solution. We only have the definition to go on, right? So we have nothing else. So we know that, I mean, later we'll learn some simplifying rules, but we're working with the definition, so that's the point of this. So we know it's got to be this. Okay, and then we put in what we have. So we know what the function is. It's 1 over square root of x minus 1 over square root of a over x minus a. And when we have stuff like this, where we have different denominators, the obvious thing to do is to make the denominators the same. So we multiply top and bottom by square root of a here, and square root of x here, to get this. And this guy, let's write it out here. Okay, so that's what we've got. And we don't like square roots, and we know this trick, right? So if you do c minus b times c plus b, this is the difference of two squares. This is c squared minus b squared. And that's a very useful trick to get rid of something like this, where you have the difference of square roots, because we don't want to deal with square roots. So let's rewrite these factors and put the last one at the front. 1 over x minus a, and rewrite this thing, square root of a minus square root of x over root x root a. And then let's multiply this by square root of a plus square root of x over square root of a plus square root of x. Right? Because this is just multiplying by 1. And then we can multiply all this stuff out, and we'll have some simplification. So multiplying out these two guys here, applying this stuff, what are we going to have? We're going to have a minus x, and we've killed the square roots. Underneath we have x minus a, and we have this stuff, square root of x, square root of a, and then we're going to have square root of a plus square root of x. Yeah? And we see that this a minus x cancels with this x minus a, and it's just going to give us minus 1, because we're going to take the limit. Damn it. So let's get rid of this equal sign. We're going to take the limit when x approaches a. So right now, this is just some algebra. But when we take the limit as x approaches a, so limit as x approaches a of this stuff, 1 over square root of x minus 1 over this over x minus a, then x is definitely not equal to a, so then we cancel this and get a minus 1. So this is equal to the limit as x goes to a of minus 1 over square root of x, square root of a, square root of a plus square root of x, right? Cool. And then it's just the limit of these quotients, right? So on the top it's just constant. On the bottom, this guy, square root of x, in its domain, a is positive. This will just be square root of a, because square root is a continuous function. We just put in the value directly to find its limit. Same true for here. So as x tends to a, this thing is just minus 1. And here we're just going to have a, and we're going to get 2 of these guys like this. So what's this? This is minus 1 over 2, and this is a to the 3 over 2 at the bottom here. But let's write it like this. And that is what we know the answer is, right? So from the mechanical rule, you know from just differentiating powers of x. If you differentiate x to the half, then you have minus a half x to the start again. If you differentiate x to the minus a half, you have minus a half x to the minus 3 over 2, which is what we've just found out, right? So f prime of a equals minus 1 over 2, a to the minus 3 over 2. Yeah. And if you take, I mean, you have homework exercises like this. If you take arbitrary, not too difficult expressions, you can just push it through and ultimately find the answer. This would be a harder type exam free response question, but it's not inconceivably harder. And this stuff, all this stuff is just algebra, which you should know coming in here. This is stuff you should be able to fight your way through to find some meaningful expression from this. And if you can't, then you just practice it until you do. Okay, so that is calculating the derivative from first principles. That is something you need to learn. And this is something, yeah, I mean, I guess it's with a very high probability you're going to face this in some exam, because we need to test that you understand the concept of derivative. So I've created perhaps thousands of free response questions testing this concept of derivative. And again, many, many times, there is some completely nonsensical formula for the derivative because somebody has got any picture about what it means. They've just memorized a bunch of symbols that mean nothing to them. But this picture is very, very clarifying for this. I mean, this is just the language describing this, right? So this is the real thing, and this is the language describing it. No one should get this wrong. This should, if you take nothing else away from this entire course, at least know the definition of derivative, be able to draw the pictures and explain what it is. Okay, so that is calculating derivatives from first principles. Now let's talk about another example of the way derivatives describe things in the world. So let's change color perhaps. Example. So we have a industrial plant which is manufacturing a bolt of fabric. So a bolt just means this long kind of strip of fabric of some fixed width. Okay, it doesn't matter what it is. And its length is x. So if you are some clothing manufacturer, you buy bolts of fabric, and perhaps very long ones, perhaps a bolt of fabric of whatever, 1,000 meters long or something, perhaps even longer. And if you are a textile manufacturer, you manufacture these bolts of fabric. So they come in these like rolled bolts of fabric, and it goes on some machine and unrolls, right? So this is our situation. So f of x is the cost of producing bolt of fabric of length x. So this is the question 1. What is the meaning, I should let me say, what is the physical meaning of, or what in this context of f prime of x? Okay, and the second question is B. Which would be bigger? F prime of 50, F double prime, not F double prime, F prime of 500, F prime of 5,000. Okay, before we start, let's try and get a grip on what is happening here. So we have some function f, and this thing here is f of x, it's the cost, right? And this thing here is the length. And our function is the cost at whatever length, yeah? So it's definitely increasing in some way, right? It's not the case that, so I'm just going to draw an arbitrary increasing function and then we'll talk about its shape in a second. It cannot be the case that as we increase the length, the cost doesn't go up, right? Nor can the cost flatten out, right? It can't be the same to manufacture, whatever, 500 meters as it is to manufacture 1,000, right? 1,000 has to be more expensive. So it is an increasing function. And it can't, it can change shape perhaps, and we'll think about how, but it definitely can't be too flat. There's always going to be some cost of manufacture, right? You can't make it, you can't bring it down too much, right? All right, so firstly, what is f prime of x? Well, f prime again is the rate of change of the quantity f in terms of the quantity that it depends on x. So f is the cost, so it's the rate of change of production cost in terms of the rate of change of length, right? So it's the rate of change of production cost over the rate of change of length. So as we make things a little bit longer, then we're going to see how much that changes the production cost. And as we make this on a smaller and smaller scale, we'll get this f prime of x, and that is the rate of change of production cost over rate of change of length, yeah, or with respect to length. So that is what this is. So solution. F prime of x is rate of change of production cost. Production cost with respect to length. So let's imagine that our graph was just like this. Then what is the derivative of this graph? It's just a constant. It has a constant slope everywhere. So that would say that the rate of change of production cost with respect to length is constant. So if you produce 500 meters of a bolt then to produce 1,000 will cost you just twice as much, or exactly twice as much, or whatever, not necessarily twice. It could be, no, exactly twice, sorry. So this has some slope m, so then in this case f would be m times x, so 500 would be m times 500 cost, and 1,000 would be m times 1,000, right? So if you double your length, you double your cost. If you quadruple the length of the bolt, you quadruple the cost, and so on. Yeah. So that could be your scenario, but it isn't particularly likely, right? Because generally there is efficiencies in scale. So for one thing, if you are going to make whatever 10,000 yards, a bolt of 10,000 yards, you're in a position to negotiate quite hard with the sellers of the basic whatever material is made out of, wool or cotton or whatever, to get a cheaper price than you would if you were just making 100, right? That's the reason Costco and other places sell you stuff which is cheaper. As an efficiency, if you're able to buy things in bulk, that's actually the reason why Walmart sells you or tries to sell you and does sell you generally things cheaper than everything else, because it's this massive chain of stores, and they can force the manufacturers to give you to sell it to them at quite a low price, right? And whereas your mom and pop, whatever grocery store in the corner, can't get nearly as good a deal. So that's one saving. Another saving is that if you are going to make whatever 10,000 meter bolt of fabric, then you might be willing to invest heavily to begin with in some very powerful industrial machinery and factory, which will be a huge initial outlay. But as you run this stuff to produce 10,000 meters of the bolt, it is overall much cheaper than simply having less automated system, hiring more people, and then paying them for a long period of time, right? So your initial, if you are sure you can manufacture a huge amount of, or sure you can sell a huge amount of something, then it's worth your while investing heavily to begin with to make the overall cost lower, and that is exactly what happens. That's why companies often try and consolidate, because they can make cheaper products this way over a long period of time if they know that they have a demand, sufficiently big demand for their product. So for these reasons, it isn't simply the case that the price is going to just be linear. It's just not going to be the case that if we double the amount of yarn we're selling, it's going to cost us twice as much. It's going to cost us less than twice as much, right? So what shape will this graph be? It'll be something like this. So your initial cost of producing, so imagine you set up some factory, you bought this expensive stuff, whatever, so you spend a lot of money to begin with, but as you produce more, and you're paying off these loans for this expensive stuff you set up, then your production costs go down, right? Because you've done the initial setting up, building the factory, buying the equipment. Over a while, after a time, you're paying less and less of the loan, you're less and less in debt, and you are gradually reducing the slope of this graph. And again, you can't ever get it down to zero, but you can make it flatter and flatter. So your f prime is gradually decreasing, right? So your rate of change of production cost per meter produced is decreasing. And this is what economists call the margin cost. So you want to obviously have as small a margin cost as possible, and that will decrease with respect to time if you've made the right choices with respect to setting things up. If you've made the wrong choice with respect to setting things up, and all you're doing is trying to do what you did just by multiplying the scale, then it won't. But if you're an efficient factory, then you will set it up so that your marginal cost will decrease. I guess that would be a good metric to determine how well some factory is performing, is how much their marginal cost is decreasing over time. Okay, so this is an example of the derivative in a completely different context. Now we're no longer talking about time, we're no longer talking about position, we're talking about cost, and we're talking about length. But this is the natural concept. This is the right thing to think about if you are an economist or a business person trying to understand the long-term profitability of some manufacturing company manufacturing bolts of fabric, right? So once again, you are forced to think about this stuff, the concept of derivative. You're forced to use the concept of a limit, and you can't well understand what is going on unless you do that. That is the reason why people in the business school study calculus, though not as serious a calculus as the one we're learning here. Okay, maybe final comment. So, if we have a function which is differentiable at every point in some interval, then its derivative itself will be a function, right? So if we took this function f of x squared, we know the graph of it looks like this, and we think about the derivative, right, which is the slope. So to begin with, over here, the slope is negative, right? And then it's less negative and less negative and less negative, and ultimately it hits 0, and then it is positive, more positive, more positive, more positive, right? So from this picture, we expect the derivative to be an increasing function, right? And we expect it to start off negative on the left-hand side, but then to gradually increase to be positive, and then to continue increasing. In fact, if we look at it more, it seems to be sort of somewhat steadily changing, right? It's changing from negative, less negative, less negative, to 0, positive, more positive, more positive, right? And we also know what the derivative is. We know it's just a function 2x. Right? Which is exactly what we expected it to be. So this is a very simple example of the picture giving us some intuition of what we expect the derivative to be like, and then we use this language of math to actually calculate it. We pre-calculated this, we know it's 2x, and the calculation confirms what the picture tells us. Yeah? And this is this kind of dance backwards and forwards from the picture to the calculation and back to the picture. This is a very cool thing. So we'll later find out, we're later going to do this a lot, that we'll have some idea, we'll express it. So we have some idea that the derivative is increasing. We express what the derivative is, that's the expression. We do some calculation, get some answer, and that clarifies what our intuition is saying and says that actually intuition is completely correct. You know? And yeah, that's some of the fun we have coming up next week. All right, so that's it for this week. Have a great weekend, and I will see you next week.